cross-cutting research, but we want to reduce those stovepipes that you all see. You definitely can see when people are pitching to a person or a program. We are really, we'd love to have more IPAs, so if you are interested and you're at that time of your career where you'd like to do some time in NSF, I didn't mean it to sound like jail time. People generally have liked it, and there are a bunch of former IPAs around the meeting here or the Earth Science meeting going on at the Hill. But if you're interested, please contact me. Just send me an email, and yes.
I guarantee you, half of this room doesn't know what that acronym is.
Thank you. Thank you for that. Yes. Speak in tongues. Yes. IPA is actually Intergovernmental Personnel Act. It's actually an acronym, but it's the rotators. So folks that come in from universities or any position, we just have to have a place where we can pay them to pay you. Come in for anywhere from 2 to 4 years and work as part of our team. And right now we have a lot of flexibility and we have a couple of open slots. So if anyone's interested, definitely get in touch. The one question that some folks are probably thinking is, whatever happens to the Antarctic Integrated System Science funding? So I need you to read that right here. That's still there. What we're going to do with those funds is we're going to use them internally as sort of a venture fund, so that if we get a big interdisciplinary system level proposal, the program officers can pull money together and get sort of venture capital from that fund. And in part we want to do that because when AISS was created, I think I was a program officer at the time, and I think we all felt like we did communicate well, we did work well together, and some of these big exciting projects we then weren't really part of. And it's really to build a robust internal team that works with these projects and helps to make continuity of program officers. So we have permanent staff and rotator staff. So that's been a concern on some of these big longer term projects, is that some of them have seen 7 program officers, and that does make it difficult. So we're trying to work a system that will get around that. As far as field related things this year, this will be the first big year of the Thwaite science. So that for us right now, as the system is just getting started, and well, I'm sure for Ted too and others in the room, is very stressful. So we're really fingers crossed that the weather and everything will cooperate, and that will go well. We have a new helo contract in place this season, which is providing us with much more capable, much more efficient birds than we had before. So I think what we'll see, this will be a good test season to see how much more effective and efficient, but I think that will be a real benefit to the field programs in the future that rely on helo support. Ames, for those that are deploying this year, you're going to see the IT&C building, which is it's the communications building. We have acronyms and I forget, I can't remember. But if you watch the webcam, you can see that going up, and they'll put a shell on that this year. And so that's sort of the pre-work for Ames, because it allowed us to move all this stuff from the JSOC building into that building. So it's the big network move, which it's pretty funny. The network there in McMurdo is better than here. And for those of you who haven't been here the last couple of days, you will soon realize that. So, but you'll start seeing this season construction around McMurdo. There's going to be maps, and it's going to be well publicized where you can and can't go. We're not giving tours of the new facilities and things, but there won't be much to tour on the short term, but you will start seeing buildings disappear and new ones going up. I know there's going to be a tendency of, oh my gosh, the weather is bad, it must be the fault of Ames, which is Antarctic Infrastructure for the Modernization of Science. I do know that one. Ames is really not south. For those that were around when we built South Pole Station, that was big impact. That used our logistics resources to build a station. Ames will not be relying on our logistics resources. So I think although you'll see things coming down that were near and dear to your heart, new things going up that you'll have to learn to love, it's not going to have the impact that South Pole has. So let's all be positive. Please. The LC-130s fleet, we are seeing that we are getting, the next couple of years, we're going to be really constrained on our availability of LC-130 mission hours. So this is a really good time to talk about future plans. It helps us better map out what the needs are in the future. But in the next couple of seasons, those hours are going to be pretty tight, which some of you are probably already hearing from the logistics side of NSF. Two more reminders. One is, remember that as you're thinking about instrumentation development and instrumentation acquisition proposals, that we have the Major Research Infrastructure Program, MRI, and that's a program that's kind of unique in NSF, where the more proposals you submit, the community submits, the more money we have access to. And in the last couple of years, Polar hasn't really had that many proposals. So those of you who are thinking along those lines, definitely remember about that solicitation. And then the last one is just the budget question. And, oh, yeah, go ahead. Major Research Instrumentation, MRI. And the deadline is usually in January, end of January. The last thing is just the federal budget. The reason we had no name on the agenda is that, as usual, at the start of the fiscal year, we never know if we'll be open for business. We were. The next is November 22nd, when we could maybe be out of business again, but hopefully not. But right now, the bill's going through the Senate, the House passed. We're looking at about an 8% increase, which is really good. That's the top of the agency. We don't know how much floats down, but traditionally Antarctic has done pretty well. Last year, they called it the Shark Tank. We got some big things funded through the Shark Tank at the end of the year. So we do tend to do fairly well out of that. So I think that's been good news for the community. And with that, that's about all the news that fits in the time that I've probably taken. So I don't know if anyone has any questions. Cool. Okay.
Okay, that's fine. Good morning. I'm Thorsten, Markus. I started as a program manager for Cryosphere about 6 weeks ago, and many don't know me here because I'm a CI scientist by training. So yeah. I think it's
You're taller than Alex.
Yeah, that's
Thanks for that.
all right, better.
Yes.
So as I said, I'm a CS scientist by training. I came to Goddard roughly 20 years ago or so as a postdoc, and then got a permanent position and stayed. And then 10 years ago, I became project scientist for ISA2, which is phenomenal, and I think you will learn more about ISA2 in this meeting. I think it's a phenomenal mission. And so I was looking for a new challenge, and Tom Wagner moved on, and I thought it's the right time to do something different, to leave Goddard after so many years and manage the Cryosphere program at NASA. So because I'm so new, I don't have that many news. The ISA2 call just closed. We got roughly 100 proposals, and I'm desperately seeking panel members.
We're all conflicted in here, Thorsten.
Well, that's exactly the problem. That's exactly the problem. So if you have not written a proposal or co-I on a proposal and are interested in altimetry, please let me know. You desperately need, panel members for the ISA2 call. Regarding the timeline, we are hoping to identify reviewers in the next couple of weeks, send proposal packages out, end of November or so, and then have a panel mid-January, and then hopefully make a selection early March or so. So that's the rough timeline for the selection for the ISA2 science team. Also, I'm working right now on the next cryo call for Roses 2020. So there will be a general Cryosphere call. I know there hasn't been one for the last several years, so I'm working on one right now. So this meeting is, the timing for this meeting is quite nice because I don't know much about Western Arctic ice sheet.
How many tens of millions of dollars will that one?
Next question. I have to see how much you can afford. Of course, I'm making it as big as I can. And there's also a chance that there will be a good likelihood actually that there will be a second ISA 2 call out in Roses 2020 as well. It will be smaller than the one that just closed, but we have to see how we go about that. But I'm very hopeful that we have another ISA 2 call out for more research-minded ISA 2. I think that's all I had really. If there's any questions for me, yeah.
The IDS call, are you involved in that at all?
So the IDS is a good one. So it closes in a month or two from now. 1 month from now. Thank you. So it has lots of cryo components in it. I'm sure it will be on the panel for that one, or some of the proposals will be given to me. It's a different part of money. It doesn't affect the cryo program. So which is great, and so please, give good ideas for interdisciplinary sciences. Please submit proposals to that one. If there's a strong Cryosphere submission, that's good for us because it's extra money. Any other questions?
You're the purely Cryosphere program manager, or do you have other programs? Because Tom had a different one that was a little confusing.
So it's I'm still the program scientist for ISA 2. Pine Mountain Azure, when Tom left, was taken over by Jared Anson, and the focus also moved a little bit away from cryo more to hydrology, so it may stay with Jared. Otherwise, I don't know. Any more other questions? No. Right. Thanks.
So we have a floating microphone for questions to make sure questions can be heard in the back. So I hadn't announced that. When you raise your hand, wait for Emma during this session to bring the microphone to you. Students will be running around doing that. So this session, there'll be 6 talks. Winnie Chu is going to be our session convener, and they'll be in typical WAIS fashion. There'll be, now 10-minute talks, followed by a 30-minute discussion about the talks. We have this beautiful tiered panel where all the speakers will sit. Winnie?
So yeah, we're going to start our first session, the dynamics across the grounding line, and Erich Larour is going to take the floor for the first talk.
Thank you, Winnie. Thank you for. Okay, so I'm going to present the work that we've recently done in the last year and a half in the ISSM team with all the co-authors in this paper. Me, Helen Cyrille, instrumental in isolation, Surrender Carey, Erich Evans, Lambert Caron looked at the genetic part of this study. Matthew Mulligan, Nicole Schlegel helped a lot supporting all the modeling. So just
That should advance.
cool. Anybody's got a laser
I have more batteries.
So the good thing is I'm the first talk, so I can put those slides of introduction and nobody gets too bored. But I think we all know kind of the context here for this. One of the points that were really interesting to us is when we have this big imprint of mass loss in West Antarctica, does that have actual ramifications in terms of sea level? And then does the sea level actually have ramifications in terms of grounding line dynamics? This is not something that people usually look at. They think, okay, sea level is an offline consequence. We're looking really at good feedback here and seeing what happens on that. really kicks in. So a lot of this was motivated by the following, the paper by Barletta, in which the GPS stations in the area were really showing some significant uplift, and I think a lot of people know this paper. The problem that we were looking at is, can we replicate this uplift with current GI models? And so we threw everything we had in our GI reconstructions in our ISSM team from Weber Caron, and we just couldn't generate any uplift that was very significant. And so this uplift has to come from somewhere. I mean, we do generate GIA models that, if you really choose the ones that are extremely aggressive in terms of uplift in Antarctica, you can generate some uplift, but it's nowhere near what was observed by in this paper. So where does this come from? Here we kind of went back to studying everything that can happen here at the grounding line. If you have an uncoupled model, which is what pretty much every IC model out there runs, you just don't even consider the bedrock uplift. You just migrate your grounding line, sea level goes up, that's it. Now, it gets interesting if you start going with more, if you look at, for example, what we call here the eustatic approach, which is basically the bathtub model. You dump ice into the ocean goes up, and you then actually lift up the ice front as the sea level goes up. That's the first thing you can do, right? The grounding line is going to go up, migrate more, and it's going to be a positive feedback. SAL, self-attraction and loading. What happens there is that because you have a decrease in local gravity from the mass loss of the ice sheet, the sea level drops close to your ice front, not the grounding line, and this actually triggers a regrounding, potentially, not a regrounding, but a negative feedback on the grounding line. Now you also have the uplift itself, and if we get this to several components of the uplift, there's the elastic one. If you just look at elastic rebound, a little bit like GIA, which is coming from previous loads, you're going to have a rebound of this bedrock crust, which therefore should reground the grounding line elastically. After that, we put the rotational feedback into place, where we know that West Antarctic ice sheet has a serious impact on, for example, the eastern seaboard in the US. Why? Because of the rotational feedback. Well, that has a tendency to bulge the ocean far away also, and so it will have a tiny negative feedback technically. And then finally, what we call the net sum model actually included a background GIA, but we did not go fully interactive on that GIA. Basically, it's very hard to right now couple a GIA model and an ice sheet model. So this, we grab whatever existed out there and we plug it directly. When you uplift the background GIA, when it uplifts the ground, it will also do quite a big negative feedback and have very significant long-term effect on grounding. So why were we revisiting this question? We really thought that something was amiss in terms of the elastic rebound, not the GIA, the elastic rebound. Why? We looked at some of the models, and if you take a grounding line retreat here of, let's say, 2 kilometers, and you model the mass loss here as a disk load on the Earth, and if you hit this guy with a 16 or 20 kilometer GIA model, which itself has elastic rebound in it, you generate an elastic rebound of about 5 millimeters, but that's about it. Model the same thing, and I'm talking like a standard GIA model with a love number approach, spherical harmonic decomposition, etc. If you hit the same model with a 2 kilometer resolution, you get a 50 millimeter uplift. So the elastic part of the GIA models were off by an order of magnitude, even more. That we thought we've got to revisit this question. And so we started, unfortunately, to do this, you have to literally model the entire Earth with a sea level model that has vertical uplift in it, self-attraction and loading, rotational feedback, elastic uplift. We did not do, as I said, background GIA. We grabbed existing GIA models out there. So we did this in ISSM with an unstructured mesh convolution. It's a pretty significant model. It's based on the Ferrell and Clark equations that were discretized in the Adhikari paper in 2017. And it's a standard convolution of the loads in Antarctica or Greenland or everywhere in every glaciated area. You just have a mass loss that actually convolves into a sea level equation perturbation, and you iterate on this and you resolve the sea level. What's interesting is we then we grabbed this, but we did we still did within this model, because we can be unstructured, a fully high-res Antarctica model. So this is actually the mesh display. You can't really tell what's going on. And even when you further down look at the Thwaites model, it's a 1 kilometer resolution. We went full out because we know grounding line dynamics needs to be solved at the 1 kilometer resolution on the ice sheet part. And we kind of had a hint that at least 2 kilometers was required for the elastic solid earth point. So we just went really full res. But we modeled the entire Antarctica continent. When we did so, we generate, most models that run West Antarctica right now generate a collapse. The timing is different. The Cyrille paper in 2017 was generating a collapse after 250 years if you push her model past the 100 years that she had presented. Nicole, you generate around 300 years, you generate a pulse. And so the timing is there. Here I generate this pulse around 350. But what's interesting is you see the kink, but then you see the reaction of the sea level generated in New York, London, Hong Kong, and Hawaii. You have different rotational feedback issues here. So they're not all the same curves, but you definitely see this split. And the split happens at the elastic model. When you include the elastic process, that's where you end up with this negative feedback, and quite significant negative feedback on sea level. Now, what's interesting is that you generate this is sea level, RSL actually, relative sea level. You do see these negative feedbacks kicking in, and we did model everywhere. For people interested, we actually represented the rest of the masses in the world using Grace extrapolated trends. So we did not go fully interactive on all the glacier masses out there, but we wanted to make sure we had the right sea level being kicked into the system. In terms of quantified impact, after a 350 year, you get a 23-year delay between the elastic component and what's currently used in, for example, in ISNIP 6. 0.12 meter negative feedback also you can quantify. What's interesting is that at a 100-year level, this feedback is only 2 to 3% in terms of impact on sea level, but on the grounding line too. Where it's really interesting also is that so I said around 350 years, you have a 30% negative feedback on sea level and a 28% negative feedback on the volume itself. So you have to be very careful when you start uplifting the ground. Everybody has to be very careful what they say when they say sea level equivalent from volume changes. It's not volume above flotation. It's complete volume, total volume. The Earth doesn't see volume above flotation. The Earth sees all the loads everywhere. You have to be very careful there. And ISNIP 6 is starting to realize this, and we're going to approach this in a more consistent way. So here it's what happens at the dynamic level is very interesting. Is you have all the curves, red here and yellow are the very aggressive curves from everything that is in ISNIP 6 right now. This is the net sum model after basically all the negative feedbacks from all these different processes have kicked in. And you see the biggest jump is from the green to the purple curve, and that's really the elastic part. So what we're saying here is that given every process that we know, I think we have misrepresented the way we quantify elastic uplift. Now, we're not saying that this is the full signal in the negative feedback. There is more negative feedbacks, and the Barletta paper suggests really viscoelastic effects. So what we're saying is that we're missing negative feedbacks from the elastic part, but we're also going to probably miss viscoelastic feedbacks from very short-term transients in vertical uplift. And this will be hit by the same constraint, this 2 kilometer resolution. And so the negative feedback, we expect it to go much higher than 30%, 350 years into the future. And we expect it to go higher than 2% at 100 years. More in our mind, probably at 20% level negative feedback. And I think this is a pretty big number and we can't ignore. And so we have to start working on these viscoelastic, fully coupled viscoelastic grounding line representations. Here is kind of an idea of what happens. A very aggressive model here. All the pinning points kind of failed and it locked into this big pinning point. And of course, you expect, even when you have bedrock uplift, that the pinning points are still going to play a role. And they do, and you see the difference in vertical uplift in the bedrock position is kind of what locks the results in these negative feedbacks and locks this grounding line with full viscoelastic rebound, with full elastic rebound into a position that is more downstream than the aggressive model. You can see kind of the rate of progression of the grounding line with the net sub model here, the full model. We get a 2500 in terms of where the grounding line is. It's fully gone into the trough and it's collapsed, generated kind of almost a mini pulse.
You got 3 more.
Here's a problem. We initially did this model with 1 kilometer of the grounding line, close to place where we had the most ice bridge data sets. We thought that's great, we can constrain. And then we said, okay, let's go 8 kilometer inland. When we did this, the model was really representing feedbacks that were completely different. So it is our strong suspicion that even at 1 kilometer resolution, we have not converged on the elastic solver. And definitely going from 1 to 8 kilometer did some serious damage. I think we had like a 30-year delay instead of a 23-year delay. We were kind of misrepresenting the negative feedback by almost 30%. And it's kind of hard to know when you downgrade or upgrade your resolution what the trend is, because it really depends on how you're capturing your pinning points and how the uplift is also represented. So I cannot tell you if you can parameterize this away using some kind of resolution constrained representation of elastic uplift. We have no clear idea right now. So there is no real magic bullet to represent this in an offline way right now. And that's a real problem in our opinion. Because running this is really intense. It takes about 24 hours on about 1,000 CPUs on one of the best clusters. So it's really not practical. But we don't see a way out yet. Here are some interesting patterns of velocity increase. It's quite blurry, so sorry I can't really see. But the velocity, you expect your typical pulse happening here, and the velocity as the grounding line retreats increases almost to 5,000, 4,000 meters per year. Here's the interesting part: the elastic uplift generated. You're looking at the elastic uplift as the grounding line retreats, and you generate here 25 centimeter per year. This is nothing on Earth that does that. There is nothing. And actually that we constrained it. We thought we're just way out here. And what were we doing? We actually took the Spadine benchmarks, plugged our velocities and our thicknesses changes, and we're spot on in terms of what we should be observing. So we're really very strong. I think there was strong emphasis on this uplift, and actually 25 centimeter we think is not your average. We have peaks at 70 centimeter per year uplift. Because there are peaks, the uplift, if you have a peak at uplift during 2-3 years, it's not going to modify your pinning point. But this over 10 years is really going to make a difference. That's a slide benchmark. So here are my conclusions, and it's not super good news in terms of modeling because we don't see a way out to parameterize it yet. Sea level negative feedback: 1% at 2100, 28% at 2350, 10% at 2500. Purely elastic, no viscoelasticity here, no GIA background, and no EBM rheology or soft rheology under the mantle of West Antarctica, which we know at 50-year timescales is going to really hit us hard and explain the Parletta GPS stations. So there's a lot of work to be done here, coupled ice sheets and solidar modeling that we thought we could get away with, but I don't think we can.
One quick question for Erich. I'll speak at once. Then we'll move on to Andrew Hoffman. It's going to talk about the impact of seasonal ocean temperature on atmosphere.
Can everybody see and hear me okay? Thank you. So I want to just start by thanking the planners of the session and of the WAIS Workshop in general. I'm going to be presenting today work that comes from many institutions and is an international project. So to start, also thank the Paul Allen Philanthropies Foundation, and then also COPRI, so the Korean Polar Research Institute. So this talk is going to focus on oceanographic observations that we have inside the Dotson ice shelf cavity. But I want to start with an ice sheet observation. So here shown is the distributed cryosat-2 swath processed altimetry time series that shows this progressive thinning inlet that starts near the grounding line, extends up the drainage, successive drainage and filling of lakes, but the overwhelmingly large signal here is thinning that happens near the grounding line. So I'm going to use this to kind of motivate discussion of kind of some of the oceanography in the Amundsen Sea. So what's driving this change is a deep warm ocean water body, circumpolar deep water. Here is a kind of climatology of this deep warm ocean water, which is concentrated just off the shelf break and then is effected onto the shelf by westerly winds. At left we have kind of depth average or depth integrated temperatures below 445 meters. And this is kind of a static representation of what the heat content of the ocean looks like for the Amundsen Sea. And then at right, we show that there's significant decadal variability in this cycle. What drives this variability is enhanced convection in the tropical Pacific. So this drives a chain of Rossby waves down that affects the wind stress at the shelf break, which then affects more of this deep ocean water onto the shelf. These observations are made across the entire ERA interim record, but interestingly, this is a monthly climatology of the same westerly wind stress pattern. We see that there's a seasonal cycle to the westerly winds. So we would expect that there's seasonal changes in the ocean heat content on the shelf. So that's what motivated an observation campaign targeting annual changes in the heat content inside a cavity. And we focus on these ocean observations. This is a summary of the survey that was conducted. These observations are made by two autonomous waterborne aircraft or watercraft. One is the Apex float. This is the same float. It's been modified, but it's the same kind of float that's used in the Argo array, and then the sea gliders. And so the Apex floats, there's a video that should play here, are actually being conveyed into the cavity using the overturning circulation of the cavity. So they ride in on the deep, warm ocean body, and then they come out, changing their buoyancy on the freshwater jet. The yellow, orange, and pink colors are the gliders. These can actually change their attitude, so they can turn and also dive, going up and down the cavity at a speed of about 1 knot. So we have a year and a half of observations inside the cavity and outside the front of the cavity that represent kind of the best observations that can ask kind of questions about the annual variability in the heat content of the ocean. So these are some preliminary results. This is ongoing work. We see very significant changes in the thermocline structure at the cavity front. And so confirming kind of our hypothesis that the circumpolar deep water is changing at seasonal timescales. We also see, like looking inside the cavity, that there's heterogeneity in the mixed layer that we wouldn't necessarily expect, and that the bathymetry in this region is much deeper than the bathymetry inferred from gravity inversions. So there's no ridges preventing circumpolar deep water from really getting all the way to the grounding line of Dotson. With these oceanographic observations, we can kind of return and re-examine existing velocities. So these are INSAR velocities that are distributed across the Amundsen Sea and are available So inside velocities from 2015 to 2019. So I'm specifically interested in the dynamics of the grounding line and whether the grounding line sees this change in the sea content of the ocean. So these are velocities, the grounding lines of Dotson, and shelf, Crosson, and shelf, and Pine Island. And we see that on annual timescales, the speed across the ground line, if we average and detrend, the speed changes and there's significant annual power, suggesting that the ice shelf and the stress balance of these glaciers is changing with the ocean. So you can do a better job of kind of considering where these changes are occurring using empirical orthogonal function analysis to this problem. So we're going to explain, we're looking at the first component, the first pattern that explains for Pine Island 86% of the total variance, and then for Thwaites Glacier 77% of the total variance, and plotted also the principal component. So if you multiply the principal component by the spatial pattern that you see, you would get kind of most of the variance explained. And we see that there's significant annual power associated with these variations, and that it's wrapped up in the same signal that is also accelerating, explaining the acceleration, suggesting that this is all a part of grounding line migration. So we can extend this analysis further. The other variable that could potentially be affecting our ice shelf velocities is the fluidity. And so these are snapshot inversions using a method called total variation that allows us to kind of quantify fluidity on spatial scales that are kind of with discreteness or discontinuities. So we actually see the propagation of a rift here on Pine Island Glacier that eventually calves in 2017. But when we average over the annual cycle, we don't see any annual variability associated with the fluidity. So we really think that this is all wrapped up in changes in the basal shear stress at the grounding line associated with its enhanced melt. So this represents kind of the conclusions and then ideas for future work. So this is again an ongoing project. These observations just finished being collected in kind of March of 2019. So again, to reiterate, ocean heat content beneath the Dotson and Crosson ice shelves varies seasonally, and that this has some kind of influence, we think, on the ice shelf velocities as things underground. So this is an image here of a static inversion that's taken but minimizes the misfit between observed and modeled state parameter, the surface velocities, over the entire time series. And so what this represents, we're inverting for C naught here, which represents kind of the friction coefficient, the mean friction coefficient over the entire time series. And what I'm interested in is then inferring the kind of a second component of the friction that changes seasonally. So more to come on this. Thank you.
I have time for some question for Andrew.
You go.
Thank you. Just so I have the oceanography straight, or the bathymetry straight, what you were showing in the solid line was the inferred bathymetry with the big sill, and then you were going like hundreds of meters deeper.
700 meters through that. Through that.
Cool.
Inferred.
That's not scary at all.
And we're working with people who are using gravimetry measurements to invert for this topography so that we can improve those inversions.
Very nice talk, by the way. What is fluidity? I really don't know.
Yeah, fluidity is the parameter in Glen's flow that represents the integrity of the ice and effective viscosity of the ice.
Andrew, thanks. You motivated the talk in part by the westerly wind stress idea. Do the data actually, can they be explained that way? In other words, does the seasonal cycle go at least roughly with that? Because there's a debate in the oceanographic community about whether that's true.
Yeah, so this is a great point. So I didn't mention space on purpose because it's something that we're still kind of trying to understand. I think modeling circulation in the across the continental shelf is going to be really important for answering this question. So timing when, I can repeat the question, timing when the shear stress then affects the warm motion water, which would then change the grounding line.
I think it'll be fine.
The phase between each of those processes is something we're still
Like if you drop it, it might turn off.
Time for one more, at least. You mentioned grounding line migration in response to ocean melting. What sort of magnitudes are you seeing at these sort of timescales?
So that's something that we do, again, ongoing analysis. The real way to infer a grounding line position is using interferometric SAR processing to look at tidal flexure. So that's those that are being processed. But independently, I'd like to see the change in the basal shear stress and inversion directly. So that's the next time we'll leave the second or next steps.
We're gonna have to move on to the next speaker, Sarah, but feel free to go chat with Andrew later in the discussion. So next up we have Sarah Neuhaus. Who's going to give us a sort of a policy perspective on the grounding line and the rocks. Thank you. Oh no, I am really short.
Yeah, thank you. Okay, good. Yeah, and I'm also a student at UC Santa Cruz, so you're allowed to judge me. So yeah, I'm going to be talking to you today about mid Holocene retreat and late Holocene readvance of the grounding line in the Ross Sea sector. You'll notice I have the word early crossed out. Our first idea was that this retreat of the grounding line occurred during the early Holocene, but the results actually indicate that it probably happened mid Holocene. So why do we care about past grounding line positions? They can. Oh my goodness. I'm only at a second. Okay. So yeah, maybe I'll just do it manually. Yeah.
You can pull the mic out too.
Okay.
Quick.
All right. Thank you very much. Sorry about that.
It's the same slide.
Okay. So why do we care about grounding line positions in the past? They can inform future ice sheet behavior. If we know how the grounding line or the ice sheet behaved in the past, we can better predict how it will happen in the future, how it will behave in the future. Ice sheet models use past ice configurations to calibrate and spin up their models. So previously, it was believed that the grounding line or the ice sheet, the current ice sheet configuration was the smallest since the last glacial maximum. However, a recent study has shown that actually this is probably not the case, and that the grounding line retreated after the grounding line or after the last glacial maximum. It sort of overshot the current grounding line position and then subsequently readvanced to its current configuration. And you can see that in this figure. The black line indicates the LGM grounding line position. Then the grounding line retreated back to this blue line and then readvanced to the red line, which is the current grounding line position. So this suggests that the Western Arctic ice sheet is actually more dynamic than we previously thought. And my goal was to try and put better constraints on the timing of this retreat and readvance in the Ross Sea. So I do that by examining the radiocarbon data that was published in that Kingsley paper, and then also re-examining basal temperature gradients that were published in an Engelhardt 2004 paper, where he had difficulty in interpreting or trying to figure out why there was such cold ice at the bottom of some of the ice or some of the glaciers there. In particular, if you look here, this is the unicorn, this red dot. He called it the unicorn paradox. He couldn't explain why there was such cold ice there. And I would like to argue that we can explain this by assuming that this was actually recently an ice shelf. So the radiocarbon data, so all of the yellow dots here represent sites where we drilled through the ice and collected sediment samples that were either underneath grounded ice or underneath an ice shelf. And we tested them for radiocarbon. one issue with radiocarbon dating in Antarctica is that there's a reservoir effect, there's an overabundance of radiocarbon dead matter. So what ends up happening is when you date something, you get an age that's older than the actual age. For example, we collected amphipods from the ocean, radiocarbon dated them, and it turns out that they were dead for over 1,000 years. So my way of getting around this is I created a carbon-14 evolution model where we examine the concentration of radiocarbon in the sediments over time using a two-phase model. The first phase representing the time when the grounding line had retreated behind our sediments, our field sites, and then phase two once the grounding line had re-advanced over these sediments. So just a little schematic. We have our timeline here. The initial conditions, we start in the last glacial maximum. The grounding line had advanced over the field sites for long enough that there is no radiocarbon present. We keep track of the fraction of modern radiocarbon, and also total organic carbon in the sediments. And you can see that for our initial conditions, there is no, the fraction of modern radiocarbon is 0 because there's no radiocarbon present in our sediments. Then we enter phase 1 of the model. The grounding line retreats behind our sediments, our field sites. The field sites are now exposed to radiocarbon and carbon-12. And so both the fraction modern and the total organic carbon increase during this time frame. And then we enter phase 2 when the grounding line re-advances over our field sites. They're cut off from the ocean. There's no more input of carbon, and the radiocarbon decays to carbon-12. I also want to point out the red star. The red star is the field sites that are currently under an ice shelf. They never enter phase 2, so we use them to calibrate the model. So these are our results for one of the cores for subglacial Lake Williams. We have on the y-axis, this is phase 1 of the model. And then the x-axis is phase 2. And for each point on this matrix, I run the model about 24,000 times. And the color that you see on this graph corresponds to the number of times that the fraction modern and the total organic carbon that were produced from the model fit within the observations. So they successfully fit the observed data. So the yellow represents the times when we had the most success in reproducing the observed data. And then this blue, I want to point out the dark blue because the dark blue is 0. So in this area here, we were never able to successfully recreate total organic carbon and fraction modern that we see in our in the sediment course. So what that does is allow us to put a minimum length of time that these sediments must have been exposed to the ocean. So the amount of time in phase 1. So for this core is about 1,000 years. This model does a nice job of allowing us to constrain how long these sediments were exposed to the ocean, but it doesn't do a very good job of telling us how long ago the grounding line re-advanced. So the way I did that was to examine the basal temperature gradients. Again, I did a 2-phase model. We have the first phase, an ice shelf. The second phase, the grounding line re-advances and we're on grounded ice. During phase 1, the boundary conditions, the temperature boundary conditions are set by the atmospheric temperature and the temperature of the ocean. We also account for basal melt at the bottom of the ice shelf, which accounts for this curve that you see in the profile. And then in phase 2, we have the same average annual surface temperature, but the bottom temperature of the ice is now constrained by the geothermal flux. So then I examined the bottom 100 meters of the ice so that we can get a basal temperature gradient, and I compare those to the basal temperature gradients published in the Engelhardt paper. So the observed basal temperature gradients. And what we have here, again, so this time we have on the y-axis, we have ice thickness at grounding. The x-axis is time. We actually ran this model from 0 to 10,000 years, but I've just zoomed in on 0 to 2,000. And the background color are the basal temperature gradients that we produce from our model. And then these lines represent the observed basal temperature gradients at the Cam ice stream, the Bin Chadler ice stream, and the Unicorn. And what we can see from these is that it looks as though the ice at these sites grounded within the last 1,500 years. So the overall picture that we're getting from these two models is that the grounding line retreats behind our field sites sometime in the mid-Holocene, and it stays retreated for at least 1,000 years, and then at some point within the last 1,500 years, it re-advances and covers up our field sites. So other studies there are other observations in this area that sort of help support this idea. First is that the Prairie ice rise grounded about 1,000 years ago, which lines up with when it looks as though the grounding line re-advanced over our field sites. Also, the Cam ice stream grounding line has been shown to have been recently further back, and it re-advanced to its current position about 400 years ago. So in conclusion, temperature modeling suggests that grounding line re-advanced recently in our study area. And then the radiocarbon dates suggest a minimum length of ocean exposure for these field sites. And then future ice sheet models should account for this in their models. Thank you.
Yeah, one quick question for Sarah. Is there Let's go first.
Thank you. That was really interesting. So you're verifying your model with bulk radiocarbon dates. How do you incorporate the geologic error in a bulk radiocarbon date from Antarctica? So you mentioned the reservoir effect, but what about all of the pre-aged carbon that is also in that sample mixed with the radiocarbon from the ocean exposure?
Yeah, so that was how we start out. I don't start with 0 carbon 12 in the model, and I actually got that number from when I calibrated the model using the 2 sites that are currently sub-glacial or sub-ice shelf. And I had to make assumptions about how much carbon 12 and how much carbon 14 were added to how much carbon 12 started there in the initial conditions and how much was added throughout phase 1 of the model. And I used I ended up using a range of range.
Okay,
Sorry.
offhand, how big is that range?
It's quite big. What is the number? It's from the accumulation rate was from, I think it's an order of magnitude, basically. Is
Okay.
what the range. Yeah.
Okay, cool. Thank you.
Thank you, sir.
Alright, next up we have Bart. I'm going to continue on this sort of paleo theme to talk about the ocean grounding zone. Yeah, absolutely.
Can you hear it? Is that working? Okay, thanks. I'm Phil Bart. My co-author is Matthew Cedar. I'd like to acknowledge the folks whose names you see here that have informed some of our thinking on this. I also would like to acknowledge NSF for the support that got us out in the field in 2015, which is a really good field season. Very, very open one. We got lots of great data. Okay, is that better?
Yeah.
Okay, thanks. And so I acknowledge the support we got from those folks and from NSF to get us out in the field. 2015, we got a lot of great data during that season. The title of the talk is on the combination of factors that influence a grounding line position in the eastern Ross Sea during the post-LGM timeframe. So here's a map of Antarctica. The gray shade shows, with the B, shows the Ben Chadler ice stream as it exists today. But here's where it was at the LGM. It expanded all the way out to the shelf edge into an area that's called the Whale Sea Basin. Here's a map of the Whales Deep Basin. It's bounded by the Hayes and the House Bank. Across that outer part, there's a saddle. That saddle represents a big grounding zone wedge, a really thick one. This is an area where there's not been a lot of study. Mussolini and Anderson used that line and those boxes or cores to reconstruct the history. Since that time, there's been a lot more data that's been acquired, including the seismic that we got. The bold line is one of those lines. And the red box is a big multi-beam survey. And we use that to make a really detailed reconstruction of the retreat, plus core. This is the seismic line that was shown with the bold line, south on the left, north on the right. It's showing the shelf edge here, and this is close to the calving front. This is that big saddle. It's a big, giant pile of overlapping wedges, at least 7 of them that are numbered down on the bottom line drawing interpretation. The dashed line is the LGM unconformity. So a lot of post-LGM sedimentation has occurred here. There are 3 little benches, and those are grounding zone wedges that unequivocally show the position of the grounding line during the post-LGM retreat. So if you look at this multi-beam survey from the outer shelf, now you're looking south, the blue is the deepest water on the upper slope, the red is the shallowest water on the banks, the Hayes and the House, left and right. And here's the line I showed you. There's the position of grounding zone wedge 1, the little bench, 2, 3, and here's their 3D projection around the basin. And that's important because we can go in and core them, that's the stop, the circles, and determine specifically when those grounding events ended. Okay. So we got a lot of information there. We also get some information about the sub-ice shelf condition, the waters that were below that sub-ice shelf, and we see evidence of an important paleo-ice shelf breakup that happened during this time frame when it was backstepping. So, let's see. So, the stratigraphic framework with the seismic, with the surface control, we can see that there was an important topographic control on those positions. And that's kind of shown here on one of the cross sections. I just highlighted the LGM unconformity with the dashed line, and here's the post-LGM sediment that overlies it. So we did that kind of correlation across the entire area for all of the seismic data. We got tons of grids, and we can construct this time depth converted map. So that's the LGM unconformity minus all of the post-LGM sediment. So if you look at that in detail, it shows at the 500 meter contour line, there's about 120 kilometers between those contour lines. But there's a bottleneck right here. And that's where all of those grounding zone wedges, the overlapping stack occurs. Okay. So there's a number of elements within the trough too. The little tiny knolls, those, and a saddle here, and it looks like the grounding lines got stuck in those places. So here's the different grounding line positions. 1 hung up on those knolls, 2 hung up on a knoll, 3 hung up on a knoll, 4 and 7 above that saddle, and just north of the constriction. And at that point, those grounding zone wedges upgraded and created that big giant pile, about 100 meters of grounding zone wedge sediment there. Also created a 4 deep in profile in the subglacial environment. So tons of topographic control. From that location, the data tells us it moved all the way back to this location. That's about the latitude of Roosevelt Island. And the data from Conway et al. 99 shows that it retreated from there at 3,200 years and moved back. The biggest retreat of the whole time happened after 3,200 years. This is a cartoon of, and I'm going to show you, this is the LGM time frame, and I'm going to show you how it moved back and built the stratigraphy of those overlapping wedges. And what's down here is a Wheeler diagram. And if you're not familiar with the Wheeler diagram, it shows distance along the surface on the horizontal. These are core locations. And then this axis is not depth, it's time. And so what I'm synthesizing in this figure is the chronologic information we have about the different timing of grounding line position shifts. So it's going to start down here at 17,000 years ago and come up to the present. The arrows are going to show the time for grounding zone wedge 1, 2, 3, 4, 5, 6, 7, and then the big shift that occurred after that back to Roosevelt. So I'm just going to let it run here. And there's grounding zone wedge 1, 2, 3. There's going to be a breakup after 4. There's the breakup occurred at 12.3, but it didn't retreat until after 800 years. And then it got hung up at Roosevelt Island for quite a long time. Looks like 8,000 years, according to our estimate. And then it shifted back to where it is now. We just saw in the last audit, probably overshot it before it re-advanced. So the other information that's probably not really obvious unless you're familiar with looking at these graphs is that there's a lot going on in this time frame. And this is when the ice stream accelerated, apparently. Okay, and put a lot of sediment in a little bit of time. That's most of that pile deposited in about a millennium. And it was post-dating the ice shelf breakup. So consistent with what we saw from Larsen Ice Shelf, Ted Scambos and his colleagues showed really well the ice streams accelerate after the ice shelf breaks up. So I'm going to go back to this figure now to show that everything I've showed you now so far has been up here. But the catchment area is actually very, very long with respect to what I just showed. And here's that image again. And that all fits into this outer 250 kilometers of that area. So within that context, all of those 7 wedges that overlap and stack is basically a grounding line position still staying for a long interval of time, about 3,000 years minimum. And then from there, it shifted abruptly at 11.3 and moved back to here. That's Roosevelt Island. The data suggests it stayed there for like 8,000 years. And according to Conway et al. 99, it retreated at 3,000, 3.2 thousand. And it moved back, and like we just saw, overshot and perhaps re-advanced. I don't know very well about what control, how it retreated to that position, if there was an intermediate step, because we don't have a lot of data from below the ice shelf. I'm going to show you cores from the outer shelf where we have some information about oceanographic condition existed below the ice shelf. And that's following on work presented by Todd Weller et al. And lots of others. This is their proposed feedback where they're showing warming drives a poleward shift of the westerlies, which creates a stronger upwelling in the southern hemisphere, which releases a lot of CO2. Within this context, we'd expect retreat of grounded and floating ice to occur at this part of the loop. So picking up on that, here's the 3 cores that I had shown with the down-facing arrows. And I want to draw your attention to this side of it. This is the delta C13 values that we took for that core in depth now. And we got benthic and planktonic foraminifera from sub-ice shelf environments. This is the benthic. And when they're within this yellow value range, it's indicative of presence of circumpolar deep water. So that data is indicating that there was intermittently circumpolar deep water circulating below the ice shelf that formed once the ice sheet started to retreat. And that was between 14.7 and 12.3. That included the time just prior to the ice shelf breakup. So it looks like that was what drove the breakup here. This is from the core that actually went right into the grounding zone wedge 7-4 set, and it too has in situ forams, and their delta C13 values are indicating that circumpolar deep water was present even after the ice shelf broke up, and you had a cow in front. So that's the Wheeler diagram, kind of showing the position of the grounding line, stepping back from the LGM shelf edge position to where it built the big saddle, pretty much a still stand, controlled by things topographic. It experienced an abrupt retreat all the way back to Roosevelt Island, hung out there a long time, and then eventually at 3.2 moved back. So I won't have enough time to talk about all of this, but I want to show you this curve from Markus et al. 2014, and showing the change in CO2 at the WDC site. And you can see there's a rapid increase in CO2, presumably related to the poleward shift of the westerlies, the release of a lot of CO2, putting circumpolar deep water close to the margin, interacting with the ice shelf. And the dashed lines show when it is that these different grounding events ended. So that's general scenario is consistent with this idea presented by Weber et al. That there was a lot of ice shelf breakup occurring during this time frame. We can say specifically that in the Whale Steep Basin, circumpolar deep water was present there during this time frame. and that included the time when there was an ice shelf breakup that occurred at 12.3, and that's also the time when, subsequent to that, 1,000 years later, that we had a big shift in the grounding line position. That's indicated by here, 200-kilometer shift from the middle shelf back to Roosevelt Island. Okay. The last thing that's shown here is the sea level curve from Peltier and Fairbanks. It looks like that big shift was also coincident with a very rapid sea level rise. That's actually meltwater pulse 1B at 11.5. So in conclusion, it looks like the data from the Whale Steep Basin suggests that there were two grounding line still stands, one on the outer shelf where the big saddle was produced, and another long one at Roosevelt Island. So that's a strong topographic control. There were also big shifts. Those still stands were followed by abrupt shifts, what looked like abrupt shifts, suggesting that there were some kind of tipping points that occurred. And in the case, at least, of the first big shift from the saddle to Roosevelt, it was a 200-kilometer shift. Looks like it occurred very rapidly. No morphologic evidence of any pauses that occurred between those two locations. And that had to be a response to several factors. And here are they. So we're arguing that it was some warming that had preceded this that drove the westerlies to the south, caused intermittent intrusion of circumpolar deep water, caused the breakup of the ice shelf. That dynamic thinning that followed that caused a lot of discharge within the ice stream, and it also created a lot of sedimentation that produced a fore-deepened profile. Eventually, during meltwater pulse 1B, the system tipped over and caused the abrupt retreat. So I'll stop it there. Thanks for catching.
Sorry, we're kind of low question time, but save your question for Philip in the discussion session. So now we're going to have Cyrille Mosbeux, sorry I butchered your last name, from Scripps. We're going to talk about the impact of basal melting on the Ross Ice Shelf.
Hello everyone, so I'll be presenting you today a work I did with Emily Glen, Peter Bromiski, Yuda Buck, and Helen Fricker with my PI at Scripps, and also Laurie Bagman and Scott Springer. We are from ESR. And it's a work about the impact of precise shelf basal melting on mass loss from West and East Antarctic ice sheets, and it's small scale changes we are looking at because it's seasonal changes. So in the last couple of months, we had like 2 papers coming out, 2 different studies from different groups, and I don't know if you saw them, but they are both about precise shelf and the impact of and high melting, summer melting on the east part of the ice shelf, really close to Ross Island. So it's 2 different studies, 2 different techniques, but they both see this high melting, and they ask this question: okay, what's the impact of this melting on the flow of Ross Ice Shelf and the stability of the ice shelf? So that's what we try to look at here. Also, in another project, Peter Bromiski and his team, they put some GPS on Ross Ice Shelf, and they looked at the displacement of the ice shelf over the season 2015-2016, and you can see a kind of seasonality where you have a displacement, so a trend of the displacement with respect to the average displacement of the GPS. So a negative trend at the beginning of the year up to April, May, and then a reversal of this movement with a positive trend. You have only one GPS station recording in the winter, of course, because it's the only one with more batteries. Okay, so the question is this movement on the ice shelf related to the melting we talked about before? And if it's linked to melting, what's the impact on the growing ice? So for that, we can use an ice sheet model. I use Elmer Ice here. I just do an initialization of my model, something really classic. We infer the friction on the growing ice between the ice in the bed and the viscosity on the ice shelf. And you can see that when we optimize those two parameters, we can get a really good agreement between the observed velocities and the model velocities. So on the right, you can see the differences, mostly because of artifacts on the observations and the kind of ice viscosity we can get on the ice shelf. When you have this initial state for the model, the ice sheet model, you can force it with Gaussian, and for that we use some output from Ram's model from Scott Springer at ESR, and we have 12 snapshots here of basal melting, so it's a parameterization of the ocean circulation in the locality, and you can see that in January, February we have a high melt, and then the melt is decreasing in March, and then really stable the rest of the year. So let's force now the model with this. And you can see that between January and February, we have an increase of the melt, and because of the increase of the melt, the shelf is responding, and we have an acceleration of the shelf. In the other way, in winter, between May and June, we have a decrease of the melt, and so the shelf is kind of slowing down. When we look at the effect of this slowing and acceleration at each GPS station, we can compute the velocity in each GPS station, where you can see that from January to April we have an acceleration and then a deceleration the rest of the year. We do it for 3 years, and you can see the seasonality. From the velocities, you can integrate the velocities in time and get displacement of the GPS. And you can compare it then with the observation. So it's model displacement in the second panel and the observed displacement in the third panel. You can see that we have a good agreement, but still some problems. First, we have so it's acceleration and deceleration phases in the model, and you can see that we have a lag between the model and the observation, about 2.5 months. So the model gets to its minimum earlier in the year than the observation. And also we have a problem of magnitude, because the model is showing an order of magnitude smaller displacement than the model, than the observation. Sorry. Okay, so what can we do to solve this? When you think about the effect of melting and the ice viscosity, in the first stage of my model, I used only an inferred viscosity. I don't change it then. It's just the inversion of the viscosity, and then we use it for the entire seasonal simulation. But actually, when you melt some ice at the base, because the ice is warmer at the base, it changes your average viscosity in the ice columns. Changing this viscosity because of summer melt with this simple equation, it's very easy. I didn't say it's the right way to do it, but basically what I do is just, I melt by so much with respect to the ice thickness, and so I change the viscosity with respect to that. And in this you have one really big unknown is the x parameter here in the equation. Let's put it at 10 here. And you can see that when I use this equation to modify the ice viscosity, I have a bigger signal in the model. So it's about, when you integrate the velocity in time again, you have about 1 to 2 meters, which is really close to the observation we have in the GPS. But again, we have a problem of lag, but in the other way this time. So the model is the model minimum is not before the observations, but now it's after, and the lag is about 3 months. So this means that changing the viscosity because of the melting will amplify the displacement of the GPS, which is good. We can have a good agreement with the observation. And it also can modify the line. So maybe changing it in a smarter way than I did, or with the good parameterization, you can have actually the really same pattern than the observations. Okay. Now, just to finish, I talked about the impact on West and East Antarctica in my title. So let's look at this. Here you have the growing line of Rosyth Shelf, and you can see the west in red and the east of Rosyth Shelf. You have a bird on the east with a high flux through the growing line, and on the left part you have the two big contributors with material and the Cedar ice shelf and the Williams and Larour ice shelf. Okay, let's look at how this average annual flux can change between winter and summer. And I have this basically where you have high flux. You can see also high peaks in the seasonal variations. But the important thing is that this gives me about 0.1% of total flux variation across the growing line. It's not big, but it's something just in a few months, right? And if we think about the seasonal pattern as something getting stronger and stronger, so the ocean and the melting getting bigger with time, we can think about this effect getting bigger and bigger. So in conclusions, we could in the model reproduce the observation pattern on the displacement of the GPS, but with a lower magnitude and a lag, but changing the viscosity, we can overcome this problem of lagging magnitude. Of course, maybe the signal we observed is not only due to observations, it's not only due to melting, or well, we have also maybe buttressing of sea ice. I don't know, we don't have much sea ice in front of Rosyth Shelf to buttress it, but maybe the wind stress is also maybe another contributor to the signal. And finally, well, we used a pattern of melting. We don't say it's the right one. It's not the right sea. It's not the same year we simulate in the RUMS model than in the year we observe on the GPS. And also, well, the seasonal variation in the model can be bigger than what we expect, or smaller. Well, we have a lot of uncertainties on that. Okay, thank you.
So while watching this slide, we can take one quick question for Cyrille.
Thanks, nice talk. You kind of addressed it at the end, but I was wondering how those ROMs melt rates compared with Craig Stewart's paper of the observations. Okay,
they look like we have a bigger signal in this corridor where you have the high melt. The ROMS model gives higher melt rate. When I look at the map, well, I don't know exactly the numbers they have in Stewart paper, but yeah, it looks like slightly bigger.
Okay. Thanks.
But then it's a local process there. We look at the entire shelf, many uncertainties in that.
Thank you so much. Next up, we have John Christian, who's a grad student from the University of Washington.
Hi, yes, I'm a student, so please judge me. I want to start by acknowledging my wonderful collaborators, and then extending a big thanks to David Pollard for modeling assistance, and also thanks to NASA and NSF for novel support. So I'll be talking about some idealized modeling experiments we've been doing to sort of probe the kind of basic constraints on fast and slow outlet glacier dynamics. So the main point that I want to make today is that ocean and interior forcing have sort of fundamentally different transient signatures on the response, and this applies both to the forced response and also to the response to natural variability. So a second point on variability is that natural glacier fluctuations depend on persistence in the climate. And then finally, we'll talk about more practical implication, which is the detection of force response. Just to sort of orient some terminology I'll be using. We've seen already in this session there's a wide range of timescales that are important. When I say fast, I'm going to mean multi-decadal. So in this talk, we'll focus on multi-decadal and longer timescales. Response will refer primarily to changes in the grounding line position and length. And then we'll be focusing on stable configurations. MEC is, of course, important, but for these analyses, it's useful to be able to think about tendencies towards an equilibrium. So we'll be starting with stable configurations. So this is our idealized setting, a very general marine terminating outlet glacier, where we have an interior surface mass balance flux. Ice is conveyed to the ocean via a combination of deformation and sliding, and then flows across the grounding line, exits the system here. And generally, flux across the grounding line is a nonlinear function of the thickness there. And in reality, there's buttressing processes that will determine sort of what shows up in this grounding line flux coefficient. So there are kind of two fundamental ways that the climate can force this system. We can either tweak the inputs, so a surface mass balance anomaly over the interior, or we can tweak the outputs, so something changes in this flux relationship, the grounding line, this flux coefficient would change. And in either case, the basic system response is to change the terminus position and modulate the output fluxes by changing the thickness of the grounding line. But we're going to ask sort of how these two different forcing types affect the transient response. So we'll use two models to explore this. The first is a simplified analytical model developed by Alex Roble and collaborators. And this model is constrained by large-scale glacier geometry and mass conservation. So it's derived by tracking three fluxes through the system: the interior accumulation flux, interior ice flow, and then flux across the grounding line. And this yields two equation dynamical system, and this can be linearized to reveal basic, the fundamental timescales of the system. So the fast timescale is on the order of decades, and a slow timescale, which for most geometries is millennia. The second model we'll use is the Pollard-DeConso model applied to a 1D flow line. This is a shallow ice and shallow shelf hybrid, and one important thing to note is that it imposes grounding line flux based on the thickness there according to the analytical solution from Christian Schupp. And so we'll apply both of these models to the same idealized test glacier. The flow line profile is shown here. This is sort of medium-sized Greenland outlet glaciers, maybe small for Antarctica. But we're not trying to simulate a particular setting, but our main focus here is on the time scale. So the two-stage model predicts for this geometry characteristic response times of about 75 to 2,000 years for the fast and slow response. So the simplest forcing we can imagine is just a step change in either in the grounding line flux coefficient or in interior surface mass balance. And so we see this long, the basic system response again is this long multi-millennial scale retreat. But if we look closely at the first few hundred years, it looks like the forcing that shows up, that comes from the grounding line means a faster initial response. So we can dig into this a little bit more if we force the system with stochastic variability. And white noise is a nice diagnostic here because it has equal power at all frequencies, so we can look at response times a function of frequency. And we see that in both cases, so we're applying the same white noise anomaly time series to either the grounding line flux coefficient or surface mass balance. And in either case, the length response is a low pass filter on these anomalies, but we can see the blues here are the grounding line forcing, and that lets a lot more of the high frequencies through. But there's also the same kind of long scale behavior for the warm colors and the blue colors. This shows up also in the power spectrum. You can see a lot more high frequency content for grounding line forcing, but again, the same behavior at kind of millennial time scales. And the two-stage model does a pretty good job at emulating these fluctuations. There's a bit of divergence at the highest frequencies, but good agreement at the lower frequencies where most of the variance is. So our sort of interpretation here, enabled by the two-stage models, we've got fundamentally a two-mode system. There's a fast and a slow mode. And what we're seeing here is that the different forcings, both of the modes have to respond to both forcings, but they project differently. And so when we have surface mass balance fluctuations that affect the slow mode first, that dominates, and the fast mode has no trouble keeping up, so we don't really notice it. For grounding line flux perturbations, the fast mode leads, but then the slow mode has to follow, and it follows with a lag. So we do still, even though we see these faster fluctuations, we do still see a lot of power at these millennial timescales too. So the slow mode is still really important for forcing at the grounding line. And so the second point that I'm going to make is that, and this gets into the importance of the slow mode, we talked about white noise forcing, but we know that decadal variability is also really important for marine intermediate outlet glaciers and ice streams. So here we'll consider the possibility of persistence in the climate forcing. So we'll consider 4 different types here. Our kind of white noise control case where we have no persistence on interannual timescales, and then 2 flavors of variability with persistence. So the first is red noise, where the variability has its own memory timescale. Here we're looking at 4 and 20 years memory. And then power law noise, where the power increases steadily as a function of frequency, and that's the blue here. So these are 200-year samples of all these different kinds of noise. We can clearly see the effects of persistence here. And we're going to normalize these so that they have the same total variance. So what we're doing is just shifting some of the power to lower frequencies in these other cases, and you can see this in the power spectra, much more power at these low frequencies. And if we apply these again to our outlet glacier models, we can see that the effect on grounding line fluctuations is pretty dramatic. So again, these are our forcing time series, same overall variance, but just different temporal structure. And the persistence alone amplifies the length variations. So we have sort of a 5 to 6-fold amplification for these more dramatic examples of persistence. And this is because we've shifted variance to these lower frequencies where the slow mode can react and is ultimately more sensitive. So I think this is an important point to keep in mind. We know that decadal variability is important. It also implies that there's power at these lower frequencies that are hard for us to directly sample, but the glacier can definitely sample these. So one example where this might come into a more practical implication is for thinking about detecting the anthropogenic force response in the context of natural variability, and what our assumption is about the persistence in the background variability. So these are just 3 cases of a trend plus noise, all with the same signal to noise ratio. We've got interannual variability in surface mass balance here in grounding line flux, and then multi-decadal variability in grounding line flux. And so these are the length responses, and the blue bars here show sort of the 1 and 2 sigma envelope for the long-term glacier variability from which the force response would need to emerge. And same forcing here for interannual and multi-decadal variability, but the persistence in the natural variability kind of inflates this envelope and is going to make it more challenging to detect the force response. Of course, these challenges are, oops, okay. This is a little bit laggy. Sorry, thanks. These challenges ultimately stem from slow dynamics and not modest sensitivity. So even if we stop the forcing, there's of course already this large committed response baked in. So I think I'm good on time. I'll just wrap up with these takeaways. We fundamentally have these kind of 2 different transient responses to different types of forcing. Persistence in natural variability is very important for the background state of glacier variability. And this is going to affect, among other things, the efforts to detect the force response.
we're gonna have a discussion panel, and I would just like to ask all of us to give a round of applause for all the speakers that came before. And also invite all the speakers in the session to sit on this glamorous table right here under the spotlight again. Well, I guess we could start from any remaining question for some of the speakers here early in the morning.
Yeah, I have a question for Phil. You mentioned a lot about the ice shelf breakup or the presence and the absence of the ice shelf, but you didn't mention what you base those inferences on, and also just the time scale. I'm assuming it had to do with the sediments you were looking at, but you didn't really talk about that.
Yeah, I didn't have time to cover it all, but we've published that work, and so we have a bed that occurs below the open marine deposits and above the sub-ice shelf deposit. That's a few centimeters thick. It shows up in 3 cores from the outer shelf, and it looks different from both of those, the overlying and underlying deposit. And we're referring that's an event bed associated with the breakup of the ice shelf. And we've got radiocarbon control just below it that says it happened after 12.3, shortly after 12.3. So some of the evidence in the unit itself includes a little spike in the abundance of chrysobites, which is a freshwater diatom. So we think there probably was some surface melting at that time, but also we see from the delta C13 values that there was circumpolar deep water circulating below that ice shelf in the time preceding the breakup. Does that answer?
Yeah.
Okay.
I have another question for Phil. So you mentioned how you could use the sediment flux to indicate an ice speed up after the ice shelf collapse that's observed with the sediment cores. Did you also consider a change in the catchment size during the deglacial period, which we know that the catchment size can change as systems are deflating and essentially like siphoning ice from other locations? So I wondered if you considered catchment size instead of ice acceleration as a control on sediment flux to the ground.
I had not considered that possibility, but I think that's certainly possible. That I'm not sure what you would look for in the interior records for that to indicate it, but what we propose is that there was a big acceleration, and the radiocarbon just really nails that down for us. So it looks like the bulk of that volume, it's an enormous volume of sediment in that composite. The bulk of it was deposited after the ice shelf breakup, and that's evident from the stratigraphic framework. So clearly there was a big giant increase in the flux.
Just to follow up on that, the sediment flux rates jump up by almost an order of magnitude. So it's very hard to imagine that you increase the area of the catchment by, I don't know, more than 2, factor of 2. So it's hard to explain, I think, Phil's observations with that.
And so this is work that's actually Slavic and I have in review right now in geology.
So I think John captured something kind of offhand during his talk, just about how many timescales of variability we have going on here. Lots of seasonal work, millennial work, century work. But then Erich started us off basically saying everything should be damped. Like we're really underestimating the elastic rebound here. And these feedbacks there's actually huge negative feedback that we're not taking into account. So I don't know, I just have had a hard time wrapping my head around that with so much variability. Are we seeing the damp variability in the paleo record, Erich? Like, and the forcings are actually much larger than we're considering?
I'm not sure I understand the question. Are you saying that the forcing response is being damped itself? I don't see why that would be the case.
The paleo record, we interpret the paleo record based on our modern understanding, but we're forgetting about a large negative feedback in the system. And so have we been underestimating the forcings in the paleo record because of that?
No, I wouldn't say that. I think, can everybody hear me?
Just bring the mic up.
Just
to
bring the mic.
discussion table.
Is it long enough?
Yeah, it should be long enough. Yeah, bring it over there.
Thank you. I don't think we're talking about dampening the reaction of the system or having higher forcings. What I think we've been missing, and I think the Kingsley paper looked at it a lot, is what happens to the pinning points. And when they go back up, they go down, but they go up. And so when you poke prairie ice rise, when you poke Henry ice rise in these ice shelves, what happens? And so that's the dynamics there. Nobody looks at, and you're going to have rotations of the flow also, and so you have all these instabilities that are going to show up. We are all focusing on Panhandle Glacier and rift and what happens. Imagine you poke an ice shelf with cork at ice rise, only cork. What happens to that ice shelf? It's going to completely rotate or do something, and on top of that, it's going to be slowed down. And same thing for prairie, same thing for other big ice rises that I'm really worried about right now. And so that is something that I just don't see anymore.
What? Oh, okay. What are you guys looking at? Sorry to put you on the spot.
Still thinking.
Okay.
Yeah, I'm going. So we heard a couple talks today that talked about the role of winds and its impact on circumpolar deep water on the shelf. But one of the talks focused on the westerlies and the shift of those, and the others was looking at what's happening near the Dotson shelf break, which is actually a band of easterlies. And so there seems to be some disconnect there between what the roles of the winds are. I didn't know if people had thoughts on what's going on.
Good question. Yeah, I think we can wait for Gemma's talk in the next session. She's going to be talking more about kind of reconstructing these winds and interpreting kind of how this affects modular circumpolar deep water. And Erich's side talk later this evening, later in the sessions too. My background is more in the glaciology, so how this kind of the observation we observe changes in thermocline structure, and so how does that affect the stresses of the ice shelf?
So yeah, in the case of the data I presented, I can't really say what the mechanism was. Simply that it looks like from the Delta C13 data of the benthic forams that there was circumpolar deep water on the shelf, irrespective of whether it was driven by a poleward shift of the westerlies, as the Togweller et al. And plenty of other folks have kind of suggested, or some intensification of the winds without a shift, or some breakup of the ice shelf. So I think there are many plausible ways, but that could put the water on the shelf and drive the retreat.
So if I can put my own 2 cents in there, what I guess I was hoping I would hear people say is that it's somewhat a question of timescales, right? That and this gets back to Matt's question as well. And I think one of the things that is useful to think about is that one has to just thinking about how the winds drive heat onto the shelf is not sort of understanding the closed aspect of the overturning circulation, which means that has to be balanced in some way by the melt and the export as well. And I think it's the adjustment to that perturbation that sets the different timescales and which aspects of the wind forcing are most important. And I don't think we understand that very well right now. And so getting at those different timescales, I think, is an important thing for this group to think about.
One of the questions I'm always wondering is, can actually an ice shelf froth dig itself a seal that is so high that it stabilizes itself? So if you're saying, like, take an ice stream and it starts accelerating, and it's kind of eroding a lot and just has this big sediment you plug in front of it, can it actually lift itself and stabilize itself out of actually being completely destabilized?
I would kind of view that sedimentation at the grounding zone that accelerated as a negative feedback, in the same way that you might argue the rebound and the sea level lowering associated with deflation might do that. Slavic might want to chime in if you were not typing over there.
But does it happen in froth or under the froth? Sorry.
Yeah.
Like, is the sediment
At the grounding zone, or
yeah.
I just will agree with Phil. I think he has it right. It's basically the same thing as rebound. You know, in 1,000 years you build 100 meters pile of sediments, and the ice on top of it is kind of protected. And that was well covered in the alley paper, science paper, like many years ago by now. So I think it's a stabilizing feedback, just like the elastic rebound is. And in this case, it took place at rates of like 0.1 meter per year or something.
on that order. Yeah. If Lauren has a question.
Yeah, maybe not a question, but a statement. So you asked whether that sedimentation happens beneath the ice right at the grounding line or in front of it, and it can happen both places, depending on if there's sediment deformation beneath the ice or if there's push of existing sediments at the ice margin. But eventually, what Phil was presenting with these grounding zone wedges is that they build up over time, and the ice overrides those features, providing essentially the same thing as rebound of the solid earth, where you facilitate local advance because you no longer have to have X thickness of ice to keep ice grounded in that position. So it's a self-stabilizing feedback, very similar to what you described. To build off the question about the presence of CDW in Phil's talk, you mentioned confirming CDW on the shelf with delta C13, but you're also presenting radiocarbon ages. So how would CDW on the shelf affect your radiocarbon ages since CDW is old? Teresa King showed this in the Amundsen sector, but I was wondering if you've thought about that here.
We thought about it, but it really makes my head spin. And so, I don't know, you're sitting next to Brad, he might want to... I'm going to throw it in your corner, because you did the radiocarbon board.
I'm a student, so obviously that's why I'm thinking about this.
Yeah. Brad, do you want to comment?
Basically, Phil and I talked about this at length when we were working on that paper, and I think that the best option that we came up with was to just use a pretty high uncertainty on the radiocarbon, on the uncertainty of the reservoir age that would encompass the few hundred years change between the CDW and the other water masses. Now, all that's based on what we observe today, right? And the CDW, its isotopic properties, are set in the North Atlantic. And there's a lot of question as to whether or not the same processes occur in the North Atlantic during the LGN and the deglacial as they are today. So I think that was the best option, was just to use a higher uncertainty on the reservoir age and just kind of smear it out. But without any independent age control, it's really hard to determine that.
Since two keywords were used, radiocarbon reservoir age, I want to comment on the question for Sarah. Basically, what people understand in the marine environment as reservoir age is the age of water in which the critters live. But Sarah did incorporate kind of reservoir age for the subglacial environment, assuming that there are some amazing amounts of dead radiocarbon in the subglacial environment, and then that the period of time when the ice shelf or the grounding line retreated past the sampling sites, the sediment sampling sites, is just the only period of time when C14 is being sprinkled into the sediments. So that question that Sarah had, that effect is incorporated in her model as the kind of indirectly through the assumption of a bunch of C12 being there. So that's one. And the other one that I want to say is I don't want the glaciologists to miss the one thing, that really interesting thing that Phil showed, which is that narrowing in the kind of valley that the ice stream was flowing in may have the same effect as having a pinning point, vertical pinning point. We kind of obsess about vertical pinning points, but forget about the other dimension, and it can be as stabilizing as a pinning point.
Just to make very briefly one thing clear that Sarah said, if it wasn't clear to everybody, the age of the amphipods, of the living matter underneath, is old. It's quite comparable to what you have in the Russet. So it's not any older underneath the ice shelf than it is in the open Russet.
And one more thing, in Sarah's model, we use the fraction modern of these amphipods as the fraction modern of the organic matter that's being introduced into the sediments.
We'll have one more question, and then we're going to have to wrap up.
Okay, so more on the model. We're talking about the amount of carbon-14 and carbon-12, but carbon-14 decays to nitrogen-14, so I'm just confused about how you're relating it to carbon-14, or carbon-12.
I have carbon-14 decaying to carbon-12.
But it doesn't matter because it's such a small amount that it actually doesn't influence.
Yeah, that's actually true. The carbon 14 that decays to carbon 12 is like 12 orders of magnitude smaller than the carbon 12.
Yeah, so actually you could assume that the C14 just disappears into empty space. It wouldn't matter.
Yeah.
Well, this is very interesting, but I want to make sure you guys at least have 5 minutes of coffee break or something. Let's thanks all the speakers.